Hey, and welcome to Unit 2. So we are finally done with sig figs and metric conversions. Now we're going to start some chemistry, and we're going to do a little bit of a history lesson today. So what we're going to look at is we're going to look at the history of the atomic model. We're going to learn where the idea of atoms started to where atoms are looking like today. So first off, I have a little timeline here, not very important to really look at, but it pretty much just has the main people, such as it has here Democritus and Dalton, what their model looks like, Thomson, his model, Rutherford, Bohr, and then the modern quantum model, which is kind of hard to see. There we go. So now you can see the modern one over here. I'm going to fly back to the other side. Okay. So let's start off where did the idea of the atom actually start? So about 400 BCE, yes, it's important to remember years because you're in honors class, so you got to know the years. And about around 400 BCE, Democritus, which is this Greek philosopher, came up with the idea of the atom. So what he did was he thought if you take something and you cut it in half, and you cut that half in half, and you keep cutting something in half over and over and over again, eventually you're going to get to a piece so tiny you can't cut it in half anymore. And he called that atoma or atomos, which meant indivisible, cannot be divided. Now we call those things atoms. But the idea of the atom started 400 BCE, long time ago, for 2,000 years ago, by a guy named Democritus, who just says that everything is made of these indivisible, uncuttable, unbreakable little pieces. Now the problem was he couldn't prove any of this. This was just a theory. This was just an idea. And it wasn't until 1808 CE, so a little more than 200 years ago, that John Dalton was the first to prove atoms existed. So John Dalton over here, who I call Big Chin Guy because he got this really pointy chin, in 1808 he proved atoms existed. And he had 3 conclusions. Now, I personally can make this bigger and say more like 5 conclusions. In a video later on, you're going to see it says 4 conclusions. I mean, it all kind of depends on if you really want to break it down or if you want to summarize them. But here's one of the conclusions. Each element is unique and cannot be divided. To me, that's actually 2. What he's saying is every single element is different. So for example, gold is different than oxygen. Oxygen is different than carbon. Carbon's different than hydrogen. Each element is unique. So nothing else looks like the other element. Each element is unique. However, he agrees 100% with Democritus. He says atoms are the smallest things in the universe. You cannot have anything smaller than an atom. So in a way, that's kind of 2 conclusions wrapped in one. So again, each element is unique and they cannot be divided. The other part, one of the other conclusions is every element that's exactly the same element look identical. So for example, even though carbon looks different than gold, every single gold atom is exactly alike. Every single oxygen atom looks like every single oxygen atom. So every single element that's the same element, they all are identical. So all the atoms of the same element are identical. All the hydrogens look like all the hydrogens. All the heliums look like all the heliums. But helium and hydrogen look different. So each element is unique, but an individual element looks like all of its own individual elements. The last conclusion can be broken into 2 pieces again. It says atoms can join to form molecules. So for example, hydrogen and oxygen can form to make water. However, you cannot create atoms, you cannot destroy atoms. Saying what he's trying to say is in a chemical reaction, you cannot create new elements, you can't destroy elements. But elements can join together to make new compounds, like 2 hydrogens and an oxygen makes water. A carbon and 2 oxygens can make carbon dioxide. a bunch of carbons, hydrogens, and oxygens can make sugar. So elements can join together to make compounds, but you cannot destroy or create elements. So again, even though I kind of summarized it in, there we go, 3, it's really 5, there we go, 5 conclusions. Each element is unique, so each element looks different than different elements, but if it's the same atom, the same element, they're all identical, so there's 2 right there. Atoms cannot be divided. Atoms are the smallest things. You cannot create or destroy atoms in chemical reactions. It's weird that I was going like that. There you go. And then the 5th one is atoms can join together to make molecules. Now, what does Dalton and Democritus, what does their version of the atom look like? Well, they call it the billiard ball theory. And basically, let me move over here. Basically, what they're saying is an atom just looks like a solid sphere. An atom is a solid sphere. There's nothing smaller than an atom. So if we were in 1808 and I said, hey, draw an atom, you would just draw the following. You would go, well, maybe we would draw it. I don't know. Draw. Oh, not going to draw apparently. But whatever. I would draw in a solid circle. That's it. That's what an atom looks like, according to Democritus and Dalton. Then, in 1893, J.J. Thomson, I said 1893, 1897. Some textbooks do say 1893 though. So it's all around the ballpark. In 1897, Thomson did an experiment using what's called a cathode ray tube, which actually used to be in old televisions. Old, those big, bulky televisions. And what he discovered this green beam that was attracted to a positive magnet and repelled from a negative magnet. Since it was attracted to the positive and repelled from negative, it showed that this green beam had a negative charge. And he called these electrons. And by finding the mass, he noticed that it weighed less than hydrogen. Now, hydrogen was the smallest atom at the time. There's nothing smaller than hydrogen. Well, if this weighs less than hydrogen, this showed that there was something smaller than an atom. So J.J. Thomson proved that atoms could be split into smaller pieces. He proved atoms had smaller pieces. Now, besides that, since he found a negative electron, he knew there had to be a positive charge as well, which he dubbed the proton. But he did not discover protons at all. A guy named Goldstein discovered the proton. But J.J. Thomson, again, he came up with the idea like, oh, okay, so if I have a negative charge and atoms are neutral, there has to be a positive charge. So they knew there was a positive charge somewhere, but he didn't know where they were. But he, J.J. Thomson, 1897, discovered the electron, which proved atoms could be split into smaller pieces. His model is called the plum pudding model. Basically, what it is you have this big sphere, well, I don't say big, but a sphere of positive charge, which was the proton, a uniform positively charged sphere, then each electron, which had a negative charge. So in his day, plum pudding, you think of the pudding as the big positive blob of proton, and each plum was an electron. Today, we would think of this as one of 2 things. Either a blueberry muffin, where all of the muffin is the positive charge, and each blueberry is the electron, or, my favorite, the chocolate chip cookie. So the cookie dough itself is the positive sphere, and each chocolate chip is the electron. So that's Thomson's model. Then, Ernest Rutherford, who looks like Mr. Stalder in my opinion, in 1911 he did the gold foil experiment, which we're actually going to do as well. Well, we're going to do a very cheap version of the gold foil experiment. But in this gold foil experiment, he shot alpha particles, which were the nuclei of helium. So it's the nucleus of a helium atom. You didn't have the electrons, it was just the nucleus of the helium. He shot these alpha particles through a piece of gold foil. And then what he would do is he'd look to see where was the most light. And every time the alpha particle would hit this fluorescent screen, it would light up. And he noticed three main things. He noticed that a vast majority of the particles went straight through. So he constantly saw this light right here. He constantly saw a light. He knows that some of the particles veered off at very slight angles, like here, here, and here. So every so often he'd see this little speck of light appear off to the side. And then very, 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 very few particles would deflect backwards. So very rarely he would notice a speck of light bounce back here. Now he was very shocked by this. According to the plum pudding model, he would totally suspect that most of the particles go straight through, which most of them did. And he expected, because of the positive and negative charges, yeah, they'd veer off at slight angles. But he was so confused as to why in the world did some of these particles bounce back? What could have caused that? Well, the reason why most of the particles went straight through is because atoms are mostly empty space. So an atom is really just a big open area. There's just very little density in an atom. It's just this wide open area. The reason why some of the particles veered off is because of the positive and negative charges, because of the protons and the electrons. But what was so confusing and what was so revolutionary was trying to figure out, why did the particles, so few of them, bounce backwards? Well, he realized that instead of having this really uniform positive sphere, that there was actually a very, very, very dense center called the nucleus. So there's this very, very, very dense center called the nucleus, which is where all the positive was. And it was like a solid chunk. So most of the particles, when they got to the gold foil, went whoosh, right through it. Let me go like this. Whoosh, right through it. Because there's mostly empty space. But every so often, a particle would hit the gold foil and bounce right off the nucleus, which you're going to see in some videos later on. So this was revolutionary. His model, Rutherford's, is called the solar system theory. And it looked like this. If you've ever seen Jimmy Neutron, you've probably seen this symbol before. You have the nucleus, and then somewhere buzzing around the nucleus are the electrons. Here's another version. So as you see, you have the very tiny nucleus, very dense center, and then all this open space is where the electrons were. But there's a major problem here. Electrons are negative. Protons are positive. Opposites attract. There is nothing in this model that stops the electrons from being attracted to the nucleus and falling into the center. Well, we know that doesn't happen. We know that electrons don't fall into the nucleus. So what in the world is stopping the electrons from being attracted into the nucleus and falling into it? Just a couple years later, in 1913, a guy named Niels Bohr fixed this. So 2 years later, Bohr improved Rutherford's model by putting the electrons in what are called energy levels. And this is what stopped the electrons from falling into the center. So his model is called the planetary theory. So as you notice, you have the nucleus right here in the center. Let's see, scroll down here. There we go. You have the nucleus in the center, and then on these energy levels are where the electrons reside. Now, the electrons can go up energy levels, they can go down energy levels, and when they fall down, they give off light. But the electrons can never, ever, ever be in between energy levels. They have to be on the track. So either they're here, or they warp here, or on this energy level. And then they can fall back down, but they'll never, ever, ever be anywhere in between. They must always be on one of these energy levels. So that was Niels Bohr. And again, it kind of looks like planets going around the sun. So right now, if we stop and think, we have protons, we have electrons. Well, we're missing something that you should know about. Where are the neutrons? Enter James Chadwick. It's funny because in regular chemistry we figured out why the guy's name was Jimmy Neutron. I'll explain that in a second. So in 1932, James Chadwick discovers the neutron. And if you don't know, the nickname for James is Jimmy. So James Chadwick, Jimmy Chadwick, discovered the neutron. Jimmy discovered the neutron, Jimmy Neutron, and that's where Jimmy Neutron on the Disney Channel got his name. So James Chadwick in 1932 discovered the neutron, and it took a really long time to make this discovery because the neutron has no charge. It's neutral. So you couldn't use magnets like they did for the electrons to see, the positive and negative charge, because neutrons don't have a positive or negative charge. We didn't have the technology yet. So eventually, it took a long time. I mean, this is only, let's see, it's 2015 now. 1932, so it's what, 83 years? It took 83 years ago we finally had the technology to actually discover the neutron, which we knew was in the nucleus now. So his model, which I think he looks like a young Mr. Frisbee in this picture here. And for those of you watching this in the future, you have no idea who Mr. Frisbee is, but that's okay. He used to be a math teacher. Anyways, Chadwick's model looks just like Bohr's model, except now we have neutrons in the nucleus as well. So it's not just protons in the nucleus, it's also neutrons. So it's protons and neutrons in the nucleus. But we still have the energy levels. Now in the modern atomic model, so this is starting probably a little bit later on, maybe the 40s or so, we're discovering that yes, the nucleus is still the center, and in the nucleus we have protons and neutrons, but the electrons are not. The electrons are not in energy levels. They're in orbitals, and it is impossible to know, or sometimes they're called electron clouds. Kind of like here, it looks like a cloud. It's impossible to know where in the world the electron is. It's impossible to know how fast or where the electron is. We can only give an approximate guess. This is the creation of what's known as quantum mechanics, where there's only a probability of finding an electron somewhere. So somewhere in the darker region is a very, very high probability of finding an electron. And then as it gets lighter, lighter, and lighter, you're less likely to find an electron there, but there is a probability of finding an electron. So again, everything according to quantum mechanics is known as an uncertainty principle. It's all approximation. You can never say 100% certainty where something is. You can only guess. Now, where are we today? 2015. Today, we know that protons, neutrons, and electrons are made of smaller particles called quarks and sparticles, and those are possibly made of smaller particles called strings, which gives rise to the idea of string theory. And if you watch The Big Bang Theory, Sheldon Cooper, he's a theoretical physicist and he studies strings. So again, in today's model, we have quarks and sparticles, which are also made of these tiny vibrating pieces of energy called strings. So that's a very long lesson going all the way back to 400 BCE. Democritus comes up with the idea of the atom, says atoms are indivisible. Takes over 2,000 years to get technology for Dalton to prove atoms exist. He also says atoms are indivisible, but each element is different. If it's the same element, they look like the same, meaning all gold looks like all gold, all oxygen looks like all oxygen. Atoms are indivisible, cannot be broken down. You cannot create or destroy new elements, but atoms can join together to make molecules. Thomson, 1897, discovers the electron, proving that they're smaller particles. 1911, Ernest Rutherford does the gold foil experiment. His big claim to fame is finding the nucleus. Again, he notices that most particles go straight through the gold foil. Some go off at angles. Very few bounce back, which proves that atoms are mostly empty space. There's positive and negative charges, and that there's a tiny center called the nucleus. Problem with there's nothing holding the electrons from falling to the center. So, 1913, Bohr creates the idea of energy levels, puts the electrons in energy levels. 1932, James Chadwick discovers the neutron in the nucleus, which again still looks like Bohr's model. Today, we still have the nucleus of protons and neutrons, except now we don't have energy levels. Now we have orbitals and electron clouds, and there's an approximate guess as to where the electrons are. And then today, we have even smaller pieces called quarks and sparticles, and even smaller, the smallest piece of of an atom of anything called strings. And that's everything. Whew, 20 minutes.